Okay, so today we're going to look at differentiation, and if we have time, we will also look at the application of differentiation. But for now, let's start with differentiation. Okay, what is important in differentiation is that we're going to look at some of the basic rules. Then we're going to work out with some formulas. We're going to look at the slope of a curve. Then we're going to look at some derivatives, and then we're going to optimize some of our equations. And in that optimization, sometimes we will also look at things that we did last week around roots and maximums and minimums and things like that. So when we go into differentiation, just a few things that is important. So again, they're not normally giving you a lot of definitions, but if they do, just make sure that you know what the definitions of differentiation is, because they might throw that into a definition with something like what we're going to do in a week or two's time, integration. So they might nearly combine a definition of differentiation and integration. But then we're going to look at the power rule. So that's the first rule that we will look at is the power rule. Then we're going to look at exponential and log functions. So we did a bit of that last week to say what is log functions, what is exponential functions. But then today we will look at how we can differentiate them. Then we're going to bring in the chain rule, and we're going to look at that. So the first one, power rule. Second one, we're going to look at chain rule. Then we're going to look at the product rule. So important to look at the product rule, and then the quotient rule. So those rules we're going to cover. We're going to look at examples of them. Then also important is that they might ask you a question to work out the first, second, and third derivative. So that is an extra component that we will look at, and then how to nearly analyze the data when you get certain points that you need to work out. Okay, so basically what differentiation does is it works out the slope of that curve. So if it is a quadratic function, that will be a straight line. If it is a cube function, you will get a quadratic function. So whatever we're going to work out, it will always be one less degree will be the answer. So cube, if you differentiate that, it will become a quadratic function. Quadratic function, if you differentiate that, it will become a simple straight line. And you can even differentiate a simple straight line, then it just becomes a number. So that will also be where we will look at first, second, and third derivatives. Okay, so what I have included for you, and again, remember your exam is open book, so you are allowed to use any your own notes, any of my notes. So again, this is a nice slide that covers all the differentiation rules. So the first thing is, and we will definitely do that in the next slide, where we will look at the question. So when you have a constant, so a number like 5, 6, 7, 20, 100, whatever, and you differentiate that constant, it will always be 0. Then we will go into detail with the power rule, and that's the one that we use the most, is the power rule. We will look at the product rule. So the product rule basically looks at if you have two functions, then we will use the product rule. The quotient rule is when we have two functions that we divide by one another. So we will go into that detail as well. And the last one is the chain rule. So when you have a function within a function. Okay, so but we will look at all these rules in examples today. Okay, so but the one that we use the most is the power rule, and then sometimes also the product rule. Okay, so let's go into the first function that we need to differentiate. So this is our first example, and what we use here is the power rule. Okay, so, and what I also going to show you is how sometimes just by differentiating one or two of the numbers, we can get already to an answer, so that again in the exam you don't need to work through all the answers, because again your exam time is limited. So you sometimes just need some time to get to a bit more difficult questions, or questions that takes more time. So let's look at this. Let's start from the left. We start differentiating. So the first one that we differentiate is the 3x to the power of 6. So how that works with the power rule is we bring the 6 to the front, so we have 3 times 6. Then we rewrite the x, and then it becomes 6 minus 1. Okay, so that is how our power rule works. You bring that exponent to the front, you multiply it with that constant that is already there, and then you subtract 1 from your exponent. So if we just quickly work that out, we said with 3 times 6 is 18, x, and 6 minus 1 is 5. Okay, so I could now already look at my options, and I see, okay, this is 3x to the power of 5, so that is wrong. There's a x to the power of 5 divided by 5. Okay, so that one is wrong. There's a x to the power of 5. Wrong. Okay, there's 18x to the power of 5, which is correct. So that will probably be my correct answer. So let's just do the same for all the others. 4 goes to the front, so that is 4x. 4 minus 1. So if we check, then that is 4x to the power of 3. 4x to the power of 3, so that is also correct. Then we sit with the square root of x. So I first want to change that we can actually work with it. It's very difficult to know what to do if you sit with a square root. So I will rather change it automatically that I can see that x, the square root of x, is the same as x to a power of a half. So then we can do the same. The half goes in front. So we have a half x. And then here we have a half minus 1. A half minus 1 is minus a half. And so if we look at that, a half x minus a half, so that is correct. And then if we look at the constant rule as well, if I differentiate a constant, it will become 0. So that will fall away, so that our answer is option 4. Okay, so again, one can systematically work through it, and then with that, you are allowed to nearly check and see that, okay, for this one, the first one was, we could nearly get to the answer with just differentiating that first option. Okay, so that is the power rule, and you can see I have included in the slides that I will share afterwards also all the work around how to work out that question again, and all the questions that we will do today. There is a set of answers for you. Okay, so now we sit with this question. So when we look at this, it looks very difficult. It's one of those that if I look at it, I wanted to say, okay, but I probably want to use as we've nearly looked at those rules, I want to use the quotient rule nearly for this. But then one looks at it and say, but hang on, here is, in all of these are x's. So it might be that we can rewrite this in a simpler form before we just go on and use that quotient rule. Because if you look at that quotient rule, there was your first function and your second function. So it does look very similar. But let's first see if we can't make this simpler. Okay, so I would first just rewrite it again into something I can work with better. Okay, so if you now see that, that one can simplify. Okay, so we can bring that x to the half nearly up into both of that. So we can say, well, that actually at the top is 2 minus a half. And when your second function is x, remember, if you see a x like that, it always means that there's x1. So, and then we bring the half to the top, and we have that function. So now if you look at that, we need to differentiate this function, it makes it a bit easier. So let's first again simplify this a bit. So 2 minus a half is 1.5. 1.5 can be rewritten as 3/2. And this one we say, okay, cool, that is 1 minus a half. So it is x half. Okay, so that is now our new function that we will work with. So we didn't need to use the quotient rule. We first simplify, and you're allowed to do that when you have the x's that you can simplify into both. If that was something like x2 plus x over x minus 1, then it would have been a different story. Okay, then we can't just simplify. Okay, so depending on how that equation look, you can first look at it to see if we can simplify. Okay, so now we follow the same principle as in this one where we had the power rule. Okay, so 3/2 goes in front of the x, and then we have 3/2 minus 1 plus a half x a half minus 1. Okay, so that is our formula. So let's just see. Okay, we will need to simplify it a bit. But that is 3/2. So already I can check 3/2, 3/2, not 2/5, not 2/5. So there already I have only two options. So let's look. 3/2 minus 1 is a half. Okay, x a half, x a half. Okay, so those two are still correct. Then again, it's plus a half. Okay, so there plus a half, not minus a half. And then if I take a half minus 1, that will be minus a half, which we see here. So our final is option 2. Okay, so this one originally seems that we need to follow a certain rule, but then if you look at when we start simplifying it first, we actually get to use the normal power rule that we have done in the previous question as well. Again, here is a bit of a summary for you. So also written out that you can see how we can get to that question. So again, as in the previous one, here is definitely the summary for you of how it was calculated. Okay, so let's get into the next component. So we've looked at the first rule. So let's look a bit at exponential and log functions, just that when I look at some previous exams and things like that, there was not always, yeah, well, I've never seen that they ask both of it. Sometimes there's one, but nearly never seen that they will ask you a log function and the exponential function to differentiate. Um, so normally there's one of them. So the easier one nearly to look at is your exponential function. So what we do with the exponential function is we will basically say that the power of, so e to the power of what we will have, we will basically rename that e to a function. So we will say, okay, that 2x, we're going to say that is equal to u, or we can say a or b or whatever. And then what we need to do is we will differentiate that. And then your second component, your EU, will stay the same. So basically, when we differentiate that, we're going to differentiate the exponent and then rewrite that same function over again. So differentiate the 2x. So when we do that, we will use the power rule again. So when we differentiate that, that becomes 2. So if we add e to the power of 2x, that will become that 2, and then we will rewrite that e to the power of 2x again. Okay, so that is how you can see we're going to do it. So if it was a function like 3e to the power of 6x, what we will do is differentiate the 6x. So that will become 6. So you will have 6 times 3x, or sorry, 3e to the power of 6x. Okay, so that is basically how you will look at the exponential function. So it can also be that when sometimes they say 6x minus 1, but something like that, you know that if it's a constant, the constant will just fall away. So it actually just, again, become the 6. Okay, and then when we look at log functions, so basically when we get when we get a function like you need to differentiate 1 over x as we had there. So, and this can go both ways. So let's I just quickly want to make cool. Okay, so let's say we've got log of x. So need to differentiate that. So that will become automatically, if you differentiate that, 1 over x. We will, in your study unit around integration, we will also show this if we need to work back from 1 over x if we integrate it, but that comes later. How that then also becomes a log function. Okay, so another one of of a log functions is that you can have a combination of a log. So that is also important. Then on your calculators, so just to understand how your calculators also work, some of you will have a log, some of you will have lin. So those two are exactly the same. So it might also be that sometimes in the exam or in your assignments, they talk about lin x. And then that is exactly, if you need to differentiate that, also 1 over x. So just be with your functions on the calculator, just be cognizant that log and lin is exactly the same. The other thing that is important is our calculators is programmed that this is always the base of that is always 10. Okay, so that is how our calculators are programmed. So it might at a stage be that they bring in this A, so that means it is not your traditional 10. Okay, so I will show you in an example or two how we do that, but just be careful when sometimes when we did study unit 2 and 3, there was log functions there as well. And it might be just that they give you log 3 and 6 to work out. So again, cashiers and the shops actually have a nice function on their calculators where you can work that out. Not so the HB. So again, just be very careful when you work that out, especially with the sums that they just ask you about log, not even differentiation or anything like that. Okay, then the other important thing is when we need to go into first, second, third derivative. And the easiest here is an example, but I just copied it quickly over so that we can work through it. So when they ask you to work out the derivative, you will normally work out the first derivative. So you will work out that first derivative of y. So that in this one is straightforward with the normal rule that we've done. So 3 times 4 is 12. Then it becomes 3 minus 1, so it's x to the power of 2. Then it becomes minus, the 2 goes into front. X 2 minus 1, so it's just to the power of 1. Then we have 5. Remember, there's like that hidden one. So 1 times 5 is 5. X 1 minus 1, which is x to the power of 0. So we will do x to the power of 0. I'll just show now again. And then a constant will become 0. So that will fall away. So our first derivative looks something like this. Just remember that the other important thing is x to the power of 0 is 1. So anything to the power of 0 is equal to 1. So when we have here x to the power of 0, that actually means that we are calculating or multiplying by 1. So 5 times 1 stays 5. Okay, so then we do the second derivative. We'll go on till we can't anymore. So the 2 goes into the front, so 12 times 2 is 24. X 2 minus 1 is 1. The 1 goes to the front. Then it is x1 minus 1 is 0, so it is 2 times 1, and then that constant falls away, so we basically have 24x minus 2. Okay, and then we do the third derivative. So that's 3. So again, there's a 1 goes in front, so that's 24. x1 minus 1 becomes 1. So your third derivative is basically staying at 24. And that is also how we did it. If you look at the previous slide, that is what the answers was as well. Okay, if they, for some weird reason, ask the fourth derivative, so if I do something like that, it is fourth derivative, then basically derivative of a constant is 0. So your fourth derivative will just be 0. Okay, so that is also, sometimes it might look weird that you don't have a derivative, or you're not always sure what it is. So in this instance, if we went for the fourth derivative, the answer would have been 0. Okay, so then the other component that we look at is, and we've touched on it a bit last week, is we're looking at certain turning points. So last week we looked at a quadratic function, and we worked out the turning point for that with that formula. But any turning point you can actually work out with a derivative. Okay, so if we have, like we had last week, the quadratic function, and we worked out that turning point with that x is equal to, so that formula, then we would have put that x number back into y, and we got that turning point. So when we work out the first derivative of this function, we will actually get the point where it will nearly interject, or will touch the straight lines, the derivative of that straight line. So we can, for each of these turning points, when we work out the derivative, we will get the turning points. Okay, so there will be questions that we will cover that will say, work out the maximum or minimum, like we did last week as well, but now suddenly with a cube. Or work out the roots, where we suddenly sit with a cube instead of a quadratic function. So again, that is important, but we will again look at a few examples. Okay, so here is one of them. So find the values of x for which the function x to the power of 3 plus 3 x to the power of 2 as a minimum or, sorry, a maximum or a minimum value. Okay, so let's I quickly just, and again, it might be totally wrong, but just want to nearly show something like this will have, so it is a cube, so it will have nearly 2 turning points. Okay, so we will need to work out the 2 turning points, and these turning points, the only thing they want us to work out is the x value. So they don't worry what the other values is. They just want us to work out those x values. So the easiest to work that out is first to factorize. So let's quickly see what I would have done. So we need to, so if we, let me quickly just draw this on. So we want those 2 points. Okay, so we want those 2 points. If we factorized that function, we would have gotten that x, and that x. Okay, so that is if we factorized that function. We're not looking for the factorized numbers. We're looking for the turning points. Okay, so when we look for the turning points, we will need to differentiate. Okay, so we differentiate first differentiation. So x to the power of 3 becomes 3x 3 minus 1, so to the power of 2. Then we have the 2 goes into front, so 2 times 3 is 6. 6x 2 minus 1 basically is 1. And now we can simplify this a bit to say, let's take out all the x's. Oh, and we can also take out the 3. So we can take out 3x. What is left in this one is x. What is left in this one is 2. So that needs to be equal to 0. So first one, 3x will be equal to 0. And x plus 2 will be equal to 0. So x will be equal to 0. Yes, Naya. See, I think you muted. Let's see if I can quickly. Yes.
Morning, sir. Sorry about that. I'm a little bit lost there by the second last step where you say 3x and into bracket x plus 2.
Okay. So let's.
Did you divide the 6 by 3 when then you get 2?
Yes.
Okay.
So let me quickly do that again. So I think that is important. So let's let's do that step again, and then just to show you.
Okay.
Cool. And let me also, while we're now quickly redoing it, so when we differentiate that to get maximum or minimum, that will be equal to 0. Okay, so then what I did, so the first thing is nearly to say what is in these two functions, in these two terms that are similar. So the first thing I take out is there's a 3 in both. Okay, so let's do it this way. So if I take out the 3, what's left in this function is x to the power of 2. If I take out 3 from the 6, so 6 divided by 3, what's left is the 2x. Then I say, okay, but now I see here's x to the power of 2. Here's also a x. So there's actually a x in both. So I basically, the second step is taking a x out of each one. So x to the power of 2 divided by x will leave me with x. 2x divided by x will leave me with 2. And does that make a bit more sense?
Yes, it does. Thank you so much.
Okay, awesome.
All right.
Okay, so now when we need to work this out, we basically say, okay, 3x will be equal to 0, or we can say that x plus 2 will be equal to 0. So, and again, why we can do that is we know when you multiply by 0, your answer will be 0. So then it's easier to just say, okay, well, that 3x can be 0. Then we don't worry about what the x plus 2 is, because it will automatically be 0 because you multiply it. Or the x plus 2, if that is 0, then again, we don't worry what the 3x is, because the x plus 2 will be 0. So anything times 0 will give us 0. So 3x equal to 0, that is x will be equal to 0. So we can already check x0, 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 option 4 is not. And then x plus 2, so we keep x on the left hand, we move the 2 to the right hand. When it's plus 2 on the left, we move it over, it becomes negative 2. So our second answer is x is equal to minus 2. So there's minus 2, so that is the answer that we want, not positive 2, not negative 6. So option 1 will be the one that we want. Okay, so that is the process, but again, I've added a nice piece of commentary as well to how to solve this one, so that you can look at that as well. So again, I'm going step by step how to calculate it. So just again, added some of the commentary and the method again, for you to look at. Okay, so that is where we basically worked out that maximum and minimum numbers. Then this is actually a question that we should only cover in the next session. But I thought let's just look at it. So here they talk about total cost, marginal cost, and what we need to do with total cost to move to marginal cost, we will need to differentiate it. Okay, so we will in the next session we will look at that where we move from total cost to marginal cost. So what we do is we need to differentiate. So to get, and let me quickly, so to get marginal cost, we will need to differentiate total cost. And the reason why I included it in this one is just to nearly show already some of the application. So we will go into much more detail in the next session around application, but just wanted to nearly show how we're going to do this. So when we look at differentiating this function, we follow the same process. So we will go, okay, 3 goes to the front, 3 times 2 is 6. We'll have Q3 minus 1 is 2. The 2 goes into the front, so minus 2 Q, that will become 1. There's a 1, so that goes to the front. It will be 80 Q1 minus 1, which then Q0, which means that Q will fall away. And then we have 150, and if we differentiate that, it stays 150. So now we have our marginal cost function. Now the next step that they ask us is, so what is this marginal cost when Q is equal to 10? So now we just replace the 10 into our formula. So we can do that. So what we then get is 10 times 10 is 100. 100 times 6 is 600. There we have 2 times 10 is 20, so minus 20 plus 80. And let me just get my calculator. So 600 minus 20 plus 80 is 660, which is option 3. So first, we needed to nearly see, and we will cover that next week extensively, when we need to work out marginal cost. We differentiate the total cost function, and they have given us the total cost function. So again, they can't ask us to work out marginal cost but not giving us the total cost function. And then they said, so when you have now worked out this marginal cost function, what will that marginal cost be when the quantity is 10? Okay, so then we substitute the 10 into that to get our final answer. Again, they are very sneaky. So if you have used this function from the start, and if you have then put in 10 into that function, you would have actually gotten 2850. So again, that's why I just wanted to bring this in with this section, because we are busy with differentiation. So I just wanted to show what we will do next week around looking at moving from total cost to marginal cost, total revenue to marginal revenue, all those kind of things we will look at next week, because again, that is quite a big section that we will need to go through. But then just the application for today. And again, I have included the whole way of doing it so that you can look at marginal cost. So marginal cost, as they say, is defined by the differentiation of total cost, and then they work it out exactly how we would have done it. But again, I just thought it's nice for you to have this piece that you can also work through it. Okay, and the last one is again a derivative that I included that is nearly a combination of things. So again, I thought let's just make sure the last one that we do on derivatives, that when we look at it, that first again I will show how we might quickly get to an answer by eliminating, but important nearly is this third one, that even if we get an answer by the second one, I want to show you also how we work out the square root of a cube. So let's do the derivative. So the first one is normally the easy one. The 2 goes into the front. X 2 minus 1, so it's just x to the power of 1. So let's look at options. So 2x, that's correct. 5x, no. 2x, yes. 2x, yes. So we're still sitting with 3 options. Then the second one, 5x to the power of 1, so the 1 goes in front. X 1 minus 1 stays 1, so our second term is 5. So let's look at it. Yes, yes, and yes. Okay, so at the moment we have only eliminated that one, which is not always too great, but at least we have 3 options left. Okay, so then we need to differentiate this one. So that automatically tells me that we will have another. So that's why we can also nearly eliminate the first option. Okay, so when we get this, I will first rewrite that. So remember, if I had just the square root of x, it would have been x to the power a half. So we'll use that same one, power half, but at the top we've got 3 times 1. Okay, so that is nearly how that would look, is we can rewrite that as x to the power of 3 over 2. So I just wanted, let's just do a few different ones of this, so that I just want to show you also how we can just so any number, so it doesn't just need to be that hidden 2 that we can have any other. So what happens is, and how I see it, to make always more it much easier for myself to look at it, is I see it as 4 divided by 3. So that is how I will rewrite that now a bit better. But this one then 6 divided by 5. So that is a way that I normally remember it. So how I remember it is we use it as 4 divided by 3. So it would be 4 divided by 3. The same with this one. The same with this one is 6 divided by 5. 6 divided by 5. So if we relook this one after that explanation, we could have again said, okay, that's x 3 divided by 2. And so that is just, I thought I wanted to show you that one, because sometimes they show us weird roots and then one is very confused, or it's like you haven't seen any of that before. But actually it there's a nice easy way to make it simpler for yourself. Okay, so that I just wanted to show you how sometimes it's just easier to look at it, and if you want to transform that into something that you can actually work with, look at it as that number divided by whatever number is in that bucket, as I so called it. So now it's much easier to differentiate that, because now it is 3 over 2 that goes to the front. So just by that, we already look at 3 over 2, and we see, okay, it's not a half, it's 3 over 2, so our right answer would be 4. But let's look, 3 over 2x, we need to subtract 1 there, so we are left with 3 over 2x to the power of a half. And then again, as we've seen, so x to the power of a half is the square root. So we can rewrite that again as 3 over 2 x square root, which is that answer. Okay, so this one I just wanted to make sure, and that's why I added it for us to work through, so that if you get something like this and you need to differentiate, that you know that there is a nice way of transforming that, where is it, that root into a number that one can work with. And again, you'll see here is a way that we can, again, so what they did is at the start they simplified it, and then they differentiate. So that's also a way that you can do it, is to say, well, let's differentiate that at the start so that we can simplify it from the start. Okay, so I just changed it up a bit to say, let's start differentiating to see which one we will drop out, and then when we have that last one that we still need to do, I just showed how we would do that. Okay, so that is differentiation. So next week we will go into the application. So I have it here, but again, it's a lot. So next week we will go into the application. So we will go into how to go from total revenue to marginal revenue. So that is, we now have done one of those examples, but next week, because it is again quite a lot of slides to go through, so next week we will definitely focus on the application of differentiation. Again, I think that's quite important, and we will not have enough time today to cover that. So I rather want us to focus fully on that next week, because again, we will go into how to work out your marginal, and that should be marginal. So let me just quickly change that, not margin. We will go into elasticities. So I think that is quite important. So, and again, it's taking that, what we did in study unit 1 and 2 when we looked at the linear equations. Now, in next week, we will look at elasticities for nonlinear. So again, very important nearly to take that next step from where we did elasticities in chapter 2. Now we will look at elasticities for nonlinear equations in chapter 6. So again, want to work through that, because it is a bit different, because again, it will look at how we differentiate functions and then work out the elasticity. So it does bring in a bit more of a different angle into that. Okay, but that is then for next week. So next week we will fully focus on the applications of differentiation and work through that. Okay, so again, I will share the recording and the presentation, and thanks Neo for joining. And again, you were only one that joined today, so I just want to say thank you for that, for joining on a Saturday.
Thank you,
Um,
sir.
cool, and
Okay.
have a great Saturday and weekend, and we will chat again next week when we unpack the application of different